Hello everyone, welcome back to course on Computational Fluid Dynamics. This is Sai Kumar, Assistant Professor, Department of Aeronautical Engineering, MLR Institute of Technology. So today's our session is on understanding the physical meaning of substantial derivative and divergence of velocity. So these are the session outcomes. At the end of this session, we will be able to understand what is substantial derivative, what do you mean by local derivative, what is convective derivative, then we have expression for divergence of velocity and meaning of divergence of velocity. So let us begin with substantial derivative. So to understand the meaning of substantial derivative, let us consider an infinitesimal fluid element which is moving in space as well as time. So since it is moving in space and time, the velocities, that is x component of velocity, is function of x, y, z and t, where x, y, z represents the spatial coordinate system and t represents the variations with respect to time. So similar to the x component of velocity, we have y component of velocity, y component of velocity and z component of velocity. So three velocity components we are going to consider because it is a three-dimensional space and the element is moving in the space at various instants of time. So the dependence of that particular velocity is represented in terms of time. So you can say velocity is a function of both space as well as time. Similar to velocity, we can consider density, which is also a function of space and time. So throughout the flow field, the density is assumed to be a function of space as well as time. So since the density field is considered as function of space and time, we can consider at time t1, if you refer to the previous image, at time t1 we can represent density as rho1, which is function of spatial coordinate system x1, y1, z1 and time t1. Similar to this, at time t2 we can consider rho2 as function of x2, y2 and z2 and time 2. So these two are densities at various instants of time, that is t1 and t2 respectively. Now let us try to apply the Taylor's theorem to the current scenario. That is, if we have considered the fluid which is traveling from one point to other point, that is from t1 to t2, where you have x1, y1, z1 as the spatial coordinate system. Similar to that, we have x2, y2, z2 as spatial coordinate system at time t2. So when we apply Taylor's theorem to this particular scenario, we can write rho2 as rho1 plus dou rho by dou x, which is variation of density with respect to space x, that is direction x, then total direction travelled is x2 minus x1. Similarly, the variation of density along y direction is given by the gradient dou rho by dou y, and gradient into the distance travelled is nothing but the total change in density with respect to y direction. Similarly, the density gradient, that is dou rho by dou z into z2 minus z1, which is again gives change in density with respect to z direction. Similar to that, since if we consider flow to be unsteady, so the density will vary even with respect to time. So the variations of density with respect to time is given by dou rho by dou t into the time period for which it has travelled, so t2 minus t1. So when we are considering this, we are trying to neglect the higher order terms to make our conditions very much simple. So we can neglect the higher order term. So by neglecting the higher order terms, we can restrict our solution only to these variables. Now let us divide this equation with respect to time and rearrange the term density. So I can write this as rho 2 minus rho 1 is equals to this whole part on the right hand side, and we are neglecting the higher order terms to be 0. So by doing this, we can end up with the equation such as rho 2 minus rho 1 by T2 minus T1 is equals to dou rho by dou x into x2 minus x1 by T2 minus T1, then dou rho by dou y into y2 minus y1 into T2 minus T1, then we have dou rho by dou z into z2 minus z1 by T2 minus T1. Again, dou rho by dou t, since it is T2 minus T1 by T2 minus T1, we can cancel them. So you will be ending up with this form of equation if you divide it with time. Now let us apply limits to these conditions, that is limit t tends to or T2 tends to T1, that is if T2 tends to T1, that means the time step is very small. If time step is considered to be very small, then T2 is approximately equals to T1. In that case, the time step will be very small. So for small time step, we can consider density as d rho by dt, that is change in density with respect to time can be considered as d rho by dt, and similarly the change in x component is x2 minus x1 by T2 minus T1. This can be written as dx by dt, which is nothing but change in or time rate change of displacement in x direction, which is nothing but the velocity component. Similarly, if we are considering y2 minus y1 by T2 minus T1, so this is nothing but displacement in y direction or change in displacement in y direction. So we can write it as dy by time as dt, which is equals to velocity, that is velocity component in y direction. Similarly, we are doing it for z direction, which is given by w. So u, v and w are velocity components. So the previous equation we can write it as, now we can reduce the previous equation wherever we find these terms, we can replace these terms with u, v and w respectively. So your equation will now get reduced to d rho by dt, which is nothing but rho 2 minus rho 1 by T2 minus T1 with limit T2 tends to T1 or T2 minus T1 tends to 0. In any of the cases, we can replace this with this. Similarly, for u has been taken from x2 minus x1 by T2 minus T1 limit T2 tends to T1. Similarly, y and z component of velocities. So your overall equation can be now replaced or can be rewritten in the above mentioned form. Now we can consider d rho by dt, which is nothing but the substantial derivative, or d by dt can be written as dou by dou t plus u into dou by dou x. If we consider these functions or variable, that is density is removed from the above equation, will end up with u dou by dou x plus v dou by dou y plus w dou by dou z. So you can write the substantial derivative as d by dt of dou by dou t plus v into divergence of v, where divergence of v is nothing but u dou by dou x plus v dou by dou y plus w dou by dou z, where divergence we call it as nabla. The symbol is called as nabla. So this symbol will be using for the divergence. Okay, so d by dt is equals to dou by dou t plus v into divergence of velocity. So here we can see that d by dt is nothing but the substantial derivative, and dou by dou t is called local derivative, and divergence of v or v into divergence is nothing but the convective derivative. So it will be looking after in the next slide. So d rho by dt, as I said, is called substantial derivative, which is physically the time rate change of moving fluid element. So it gives total change in the moving fluid. So if we are differentiating with respect to d by dt, any variable, if I say d by dt, it is nothing but acceleration. The total acceleration can be found out. D rho by dt, total change in density with respect to time. So it includes both the terms, that is local term or local derivative as well as convective derivative. The local derivative is nothing but changes with respect to time. The local derivatives are nothing but changes with respect to time. So these are physically the time rate change at a fixed point. So the input at any given instance might be changing. So those changes in the inputs itself will be considered as the local changes. So those local changes are represented by the local derivative term. Whereas we have divergence term, which is called as convective derivative. So convective derivative physically means the time rate change due to movement of the fluid in the space from one location to another location. So since we have considered a element which is moving from this point to this point, t1, t2. So at the same time it is traveling from x1, y1 and z1 to new space coordinates, which is x2, y2 and z2. Because of the transition from this point to this point, there are certain changes. So those changes are called as convective derivative terms. So divergence of velocity, you can call it as the time rate change incorporated in the fluid element due to change in its position from one point in the space to another point. So this is about the physical meaning of physical meaning of substantial derivative. So we'll end the session today, then we'll meet in the next session. Thank you.